semi-plenary talk from Mohammed Cherif Kihal. So actually it's a contribution from North Africa. I'm really happy that he could join us in the European, Middle East, and Africa part of the conference. So Mohammed, I've seen that you're a lecturer researcher in the University in Algeria. I'll not try to say the name of the university because I do not think I can pronounce it properly. But also you had studies in the University of Nottingham in France, right?
Yes.
Okay,
I'm from I'm a lecturer from the University of Jijel in Algeria.
Yes, perfect.
Yes.
I'm glad that and I'm looking forward to your talk on near field
measurements.
Yes, near field measurement. Yeah, can you share your screen?
Okay. Can you see my slides?
Yes, yes. Actually, just one reminder to everyone. After this talk, please, I would invite you to all go to Gather Town to check out the posters. A lot of people will be there, so please, after the talk, come join us in Gather Town. Okay, Mohammed, please, can you start?
Okay. Okay, great. All right. Well, thanks for the introduction. So I'm very happy to be here virtually to tell you a little bit about my recent work. First of all, I would like to thank the organizer of the conference for inviting me to give this talk. Today, I'm going to present the work that we did between the University of Jijel, the University of Science and Technologies Houari Boumediene Argis, and the University of Nottingham. Then I will present an overview of near-field measurements and inverse modeling methods. So before I start, I acknowledge all the people who contributed in this work, especially Professor David Thomas and Chris Smart from the George Green Institute of Electromagnetic Researches. Okay, I would like to tell you what you should take away from this talk. The motivation of this research is really to find low-cost ways to characterize electric and electronic systems. Nevertheless, there are several challenges. First, the time required to obtain the model is huge. Reducing this time can affect the accuracy of outcomes and limits the validity domain, which makes it hard to optimize the process. On the other hand, in the conception process, we can use near-field scanning. Far-field measurement is required for the certification phases. Therefore, what I'm going to tell you about today is a modeling of electric and electronic systems using near-field measurements and inverse methods. So here is the roadmap of my talk. Then I will start with an introduction to electromagnetic compatibility. I'm going to give you some motivation about what you are interested in this topic. In the second part, I will present conventional near-field measurements, and I'm going to show you how we can improve them with an adaptive approach. In the last part of my talk, I'm going to show you how we can use this approach to model electronic and electric systems with the help of inverse modeling methods. Okay, let's start with the introduction. In recent years, the world has experienced great evolution in electronics. This evolution was at the origin of a real industrial revolution. The miniaturization of components, the increase in clock frequencies and switching speeds have made it possible to optimize system performance and provide a better user experience. However, these advances can cause coexistence problems, especially when integrating circuits of different nature in small spaces. It's electromagnetic compatibility issue. Our research fits into this context. Electromagnetic compatibility is defined as the ability of an electric or electronic device to operate in its electromagnetic environment satisfactorily without producing intolerable electromagnetic disturbances for anything in this environment. An electromagnetic compatibility problem can be divided into three actors: source, victim, and type of coupling. The objective is to develop EMC models, simple, generic, precise, and insertable into simulation platforms. In order to characterize electromagnetic disturbance and coupling, there are two ways to simulate direct simulation and equivalence methods. For the direct simulation, we must model the whole system. The knowledge of detailed modeling, physical and geometric properties is required. This approach is numerically expensive. Equivalence methods represent a good alternative that can be used to model electric and electronic systems without knowledge of details. This method is fast, have a high accuracy, and help us to find a far field by numerical and analytical calculation. Near field measurements. We start with a definition of the conventional measurement principle. We then present the idea of a sequential adaptive measurement. To better understand a near field measurement, we must answer the three questions. Why do we approach a near field measurement? How to carry out a near field measurement? Moreover, what are its limits? A near field measurement provides precise information on the radiation sources. Near field measurements have a high precision and low uncertainty. It's also less expensive and can be used in a variety of applications. How to carry out a near field measurement? To answer this question, it's necessary to specify what type of near field measurement. Generally, we can classify types of near field measurements according to the three criteria: by application domain, by configuration type, or by scanning surface. The near field measurement in the radiating zone can be used to characterize the antenna's emission, or in the highly reactive region to resolve EMI or EMC problems. By configuration, there are two variants: a single probe controlled by a precise positioning system and a planar array scanning systems. According to the scanning surface, three types of near field measurements exist: planar, cylindrical, and spherical configuration. Planar scanning is easy to implement, and its hardware and software requirements are relatively simple, which leads to high feasibility and reliability. Cylindrical and spherical scanning characterize radiation in wider range. Basic requirements and costs are higher. Then, how to carry out a near field measurement? We need several elements, such as a measuring device, for example, vector network analyzer, spectrum analyzer, oscilloscope. We need a GPIB card, is the element that connects the measuring device and the computers, a computer, a motion driver, a positioning device, probes, a coaxial cable, and of course, elements in the test. A measurement consists of collecting the data and saving it in computer for an analysis and processing phase. We often use the triggering and averaging function to maximize the precision and improve the quality of the measurement by removing noises and the fluctuations. Generally, we use LabVIEW and MATLAB to carry out a near field scanning. Two types of probes exist. The electric probe has an open circuit form and captures the electric field generated by voltages. The magnetic probe is a loop which captures the magnetic field generated by currents. The acquisition device is the most important element, is the one that is responsible for the quality and type of quantities captured. Vector network analyzer in internal mode. If the element under test is powered by external RF signals, VNA can be used by injecting a current at the working frequency of the device and measuring the transmission parameters S21. Vector network analyzer in external mode. A reference is required to obtain phase information if we want to evaluate the radiation of an active device or a complete self-power card. The method of using the external source of VNA is the most convenient way to obtain phase information because phase is directly included in complex readings. Spectrum analyzer is magnitude-only receiver. Measuring the near-field amplitude can be accomplished simply by transmitting the probe output to the spectrum analyzer. Phase information cannot be obtained directly. Finally, oscilloscope. The advantages of time domain measurements are time efficiency, wide instantaneous frequency coverage, and simplified capture of spread spectrum signals by frequency hopping. Here, the monopoly circuits is represented. The second is the configuration of the measurements, while the third presents the radiated field. This measurement is generally used to check the influence of electrical coupling on the magnetic probes. The second case is the measurement of the field radiated by a PCB. Here is the configuration of the measurement and the field in 2D and 1D radiated by this structure. What are the limits? The major limitation of a near-field measurement is the significant time. A significant amount of time may affect the cost of the measurements, can also affect the measurement accuracy through the influence of temperature on electrical components, and can lead to slow design procedure and therefore a delay in manufacturing and marketing. What are the solutions? In this section, we propose a solution that is based on sequential adaptive measurement. In uniform measurement, the spatial density is constant throughout the measurement spaces, while an adaptive measurement offers great efficiency in terms of measurement time. The fact that spatial density is adjusted according to the complexity of the field. The precision of the measurement is strongly linked to the spatial density. The density is limited by an upper limit and a lower limit, defined by the maximum resolution of the probe and the height of the measurement. The goal of an adaptive measurement is to determine the importance of measuring a specific location based on dynamic variation of the field around the point, instead of measuring all candidate points. The initial measurement is a uniform measurement with a step equal to the maximum step defined by omega, equal to twice the height of measurement. For reason of convexity, we take measurements as the edge of the domain, although they represent a weak sources of information. Here is the flowchart of the method. After defining the position of the initial measurement, we calculate the terms deviation x and deviation y for the points circled in red and yellow. If these terms are greater than the selection criterion, we consider the points as interesting points, and we take the measurements. Otherwise, we will calculate instead of measuring the field on these points. To complete the uniform grid, we use the interpolator. The aim is to find a uniform grid composed of measured and calculated points. We update the sampling step and we carry out the test. If the step is greater than minimum step, we return to the evaluation step. Otherwise, we stop the process and display the result. Selection criteria. The first criterion varies from a maximum value to a minimum value. These values are defined beforehand. The second varies according to the max values of the field gradient, while the third varies according to the average value of the field gradient. These figures present the radiating configurations and the field calculated or measured with the conventional methods. We apply our adaptive procedure. These figures show the positions of points as the last sequence for the three components Hx, Hy, and Hz, and for the three selection criteria G1, G2, and G3. We notice the difference between the points selected by the three criteria. On these figures, the maps recorded during the adaptive measurement operation are presented. We note that the field improves according to the sequences, the number of points increase, and the average error decreases. For the practical cases, here it is the position of the points at the last sequences. For three frequencies, 300, 600, and 900 megahertz. And for the three selection criteria, the same thing, we notice that the selection criterion influences the position of the selected points. These figures show the evolution of the radiated magnetic field over the sequences. The field improves according to the sequences, the number of points increases, and the error decreases. Comparison between the results. Here is the histogram of the measurements obtained with conventional and adaptive measurements. We clearly note the advantage of using adaptive measurements procedure. Time are greatly reduced. These results show that we might occur results with an error of less than 3 dB using only 10% of the uniform grid points, and an error of less than 0.5 dB with 45% of points. Now we will talk about modeling methods based on near fields. The first family is the family of direct transformation near field far field. In this method, we define the wave coefficients to find the far field from the near field. Unfortunately, the identification of the radiation sources is not of concern in this method. The second family is the modeling of the source equivalent to the scanning surface. It is based on the definition of the integral equation to find the relationship between near field and equivalent current, and on the use of the method of the conjugate gradient to calculate the far field. Unfortunately, this technique is not applicable in the half space behind the antenna. The last family is the modeling family of the real or equivalent sources to the real surfaces. This method is based on the identification of equivalent or real sources at the real surfaces by inverse algorithms. Then we can calculate the far fields using analytical or numerical methods. Several variants exist in this family, namely the manual methods is based on the manual placement of the dipole and the visual determination of the current. ECM-EBIS methods is only valid for integrated circuits. It requires ECM and EBIS models. The analytical inverse method is characterized by a high number of dipoles and by its difficulty to insertion into simulation software. The new approach is divided into two stages. The first is image processing, and the second is optimization. It's characterized by a high calculation time and less precise result compared to the analytical inverse methods. Now we are talking about the inverse method based on meta-heuristic algorithm. Instead of knowing the source parameters to predict the responses, the inverse method reversed the process using algorithms to solve the relationships between the responses and source parameters. The model is made up of a group of dipoles placed on plane. Some parameters are known beforehand, such as relative permeability, relative permittivity, frequency, and height of measurements. Some parameters are defined by the user, which are the number and the length of dipoles, and some parameters to be identified, which are the position, the orientation of the dipoles, and the intensities of the currents. This flowchart shows the principle of the method. Indeed, it's composed of three phases: extraction, verification, and validation. It's clear that it is necessary to have a model for the calculation of the radiated field. Here, the dipole model is used. According to the Maxwell's equations, we can find the propagation equations of vector potential and scalar potential. The solution of these equations is given by the delayed potentials. Using the simplifying hypothesis, propagation masking, and dipole approximation, we can find the expression of the electric field and the magnetic field. In these figures, the electric field and the magnetic field radiated by an electric dipole are represented in 3D. These figures represent the electric field and the magnetic field radiated by magnetic dipoles in 3D. The superposition method is used for calculating the field radiated by a set of dipoles, the parameters of which are displayed in this table. The result obtained are presented in these figures. These fields will be used as inputs to the inverse method. The parameters of equivalence model are calculated by applying the inverse method to the Hx component of the field. This is the extraction phases. We notice in these figures a good agreement between the results obtained by the field generator and those obtained by the equivalence model. The model is therefore verified. We notice a good resemblance between the results obtained by the field generator and those obtained by the equivalent model at a high D2 different from D1. Then the model is validated. As an example, we will test the coupling between the transmission line and an aggressor circuit. In order to use transmission line theory, line's reaction must be almost theorem, and distance between conductor and the ground plane must be very small compared to the wavelength. The line has to be uniform. A transmission line can be modeled as a series of RLC circuits. Electromagnetic disturbances are introduced into transmission line model as distributed or localized voltage or current sources. There are three equivalence models: Taylor, Agrawal, and Rashidi. The Taylor model presents the effect of an electromagnetic disturbance by a voltage and a current sources distributed throughout the line. The Agrawal model presents a disturbance by localized and distributed voltage sources, while Rashidi presents the influence of disturbance only by current sources. These figures present the magnetic field measured at 10 MHz at a height of 5 millimeters. The size of the maps is 15 by 15 centimeters. The aggressor circuit is replaced by the equivalence model calculated using the inverse methods. These figures represent the reconstructed magnetic field estimated by equivalent models. The calculation method is applied to the configuration of the problem. Here are the value of the voltages induced as the terminal of the transmission line, calculated without knowledge of the physical or geometrical parameters of the aggressor circuit. Example of a line of length 3 millimeters and line of length of 10 millimeters. Despite the fact that the process does not require the geometrical or the physical data, we notice that the variation in the physical or geometrical properties influence the results. So with that, I will conclude my talk. Together, we saw development of an approach of measuring and modeling in electromagnetism. We presented a near-field scanning system with an adaptive measurement approach for radiation modeling. The inverse modeling based on near-field scanning has also been exposed. We finished by evaluating the induced phenomena using Taylor-Agrawal and Rashidi's analytical models. This set of tools and models can be used for analysis of electromagnetic compatibility problems and make it possible through simulation or measurement to find an appropriate solution to eliminate or reduce the different type of disturbances. As perspective, we can count on automating the system of measurement, extraction and evaluation of couplings, propose solution for characterizing coupling with a non-uniform structure, develop multi-frequencies emission models. And finally, I say thank you for your attention.
Thank you very much for your talk. It was very
I don't hear you.
interesting and covered a lot
Do you hear me?
of points on the near field. Thank you very much. Do we have questions? We have quite a.
I have a problem with mic. Yeah?
Can you listen to me? Are you listening?
You hear me?
Hello? Are you listening? I guess we have some technical problems. Hello?
Hi, you hear me?
Yes, I can hear you. Good.
Okay.
Very good. So thank you very much for your amazing talk. It was quite interesting and covered very deeply the field of near field. And you have been working on that since your PhD, right?
Yes.
Good, good. And what are your future perspectives on the field? Like how do you want to proceed with your studies on the field?
We work actually. We work in the spherical measuring for the characterizing in 3D of electrical inverter.
Mm-hmm.
Then the problems is with the multi-frequency coupling or multi-frequency emission problem.
I see.
Yes.
Okay, interesting. I guess we now are on the time of the poster session in the other town. So I think we can all go to the other town and then continue with the discussions and yeah, check the posters. So
Thank
I
you.
hope to see you all. The Gather Town link is on the chat and see you all there. All right. Thank you once again, Mohammed, and
Thank you. Thank you. See you later.
Bye bye.